The following presentation is part of the Technology and the Corporation Conference Series, sponsored by MIT's Industrial Liaison Program.
All right, so I'm going to cover a couple of things today. So as you can notice in the title, which was actually provided by Randall. But anyways, the title itself, so there's an aspect of the smart and then the phone without using the cloud. So I'll focus first on the smart aspect and basically what is all this AI hype about and what does it actually entail. And then I'll move more towards how can we move that out of the cloud and into the phone, which is actually the focus of the research in my group. So to start off, if the slide would advance. Okay, I don't know why it's got scrambled. Okay, so anyways, pretend it's not scrambled. So the very first thing I'm going to talk about is basically what is deep learning. That's a specific type of AI that's become very popular. Then the second thing is talking about how can we use AI in various different applications, and then how can we move AI to the edge, which is outside of the cloud, and then how can we make that very efficient. So I'm sure you guys have all heard a lot about this whole AI artificial revolution. One particular important aspect, which is in this very large subfield of AI, is basically the idea of, or concept of machine learning. And the idea there, as dubbed by Arthur Samuel, who was a pioneer in AI, is basically the field of study that gives computers the ability to learn without explicitly being programmed. Okay, so you don't actually have to explicitly tell it what to do. It can learn from its environment or data that it's seen before and do a certain task. Now, within this whole huge area of machine learning, there's a subset of work that's called brain-inspired machine learning, and there, the idea is that they develop algorithms that are basically inspired or take from the functionality of how, as we know it, the brain operates. Okay, and then even within that, very specifically, we're talking about neural networks, and I'll go a little bit more into that, but I just want to kind of encompass that, you know, the field of AI is very large, the field of machine learning is very large, and so just because we're talking about neural networks and deep learning in particular, that doesn't encompass all of AI, okay? In neural networks in particular, this is just a very kind of high level understanding of what's actually going on. So in your brain, you contain about 80 billion neurons itself, and each of these neurons basically are connected to another, 10 to the 14, 10 to the 15 synapses. It's a huge amount of processing that's going on. If you want to break it down to an approximation in these neurons itself, all it's basically doing is what we call a weighted sum. You get some data that comes in, you multiply it by a scale, a weight, you add them together, and then you usually process it with some nonlinear function and it goes out. So if you want to think of it at the simplest modeling level, that's what we see it as. And so we can expand this in neural networks to basically build up layers of these kind of summations and nonlinearities and build different layers to do the computation and scale it up. And that's basically at the very high level kind of understand what is neural networks. Just a bunch of sums, multiplies, and some nonlinear function. Okay? And then in the scope of neural networks, there's this field called deep learning. Okay, so we've gone from very high AI all the way down to deep learning, and there's been a lot of hype about deep learning over the past few years. So let me give you a little bit of intuition in terms of what deep learning is and then how we can actually use it. So what is deep learning itself? So deep learning is actually basically neural networks, but stacked very deeply. That's the name deep learning or deep neural networks. So if we take the concept of image processing or image classification, what you can view it as is all of these circles here are different neurons that are connected together with synapses, and you have an image that comes in, and at each layer, by doing these multiplies and accumulates and nonlinearities, you're extracting certain features of the image, right? So at the very earliest layers, you're getting things like edges, right? And then as you go deeper and deeper into the layer, you're building kind of a hierarchy of these features, so soon you'll get things like wheels and car doors, and then finally at the highest level you actually extract cars itself. And then based on this you can actually tell it's the images of a car and what type of car it actually is. So hopefully intuitively you get a sense of this is what's going on. And actually so the idea of neural nets and deep learning has been around for decades. So why is it really hot now? What's the difference, right? People have been studying these things for years. So the first thing is the availability of big data, right? So these days with the internet, we're collecting a lot of data from people. So for example, Facebook has over 300 million images that are uploaded per day. Walmart has 2.5 petabytes of customer data hourly. And then YouTube has 300 hours of video uploaded every minute. And I think that 300-hour statistic is 3 years ago. So you can imagine today how much more it is. So there's a huge amount of data that's available. We can use this to train these networks, and by training I mean kind of setting the weights of these networks. To train them, it requires a lot of compute power, so the advent of basically GPU acceleration has enabled us to train these networks a lot faster now than we could have many years ago due to Moore's law and the new architectures of these hardwares. And of course, there's also new ML techniques as well. One particular good example of these large data sets is the ImageNet data set, or the ImageNet challenge. This is a challenge that's hosted by Stanford every year since 2011, or 2010, sorry. And basically, as part of Fei Li's group at Stanford, what they did was they collected a lot of data, or a lot of images in particular, so 1.2 million trained images, right? Training images, and what that means is these are labeled images. They get people to actually label and say within this image, what is the object itself? Right? And they go through this whole process of cleaning up the data to make sure that the images are properly labeled, and they're labeled into 1,000 categories. Okay? So this is kind of the first step, at least in academia, in terms of allowing to have a publicly available data set that's properly labeled that can be used for training. And so since the launch of this challenge in the first 2 years, the primary focus was on the more traditional types of machine learning, which is basically using handcrafted features. What that means is that you'll have experts in the computer vision community say like, hey, edges are important, let's design features that extract edges, let's design features that do this and that, and this is what we would kind of detect. So these are kind of the experts that come up with rules in terms of recognizing objects. Since the advent of deep learning, the idea for deep learning is that these features are actually learned by the system itself. So we could see they get these, not just edges, but these higher level features of wheels and cars, and that's actually learned directly from the data. And since then, the error rate here, so shown here on the y-axis is the error rate, so the lower the better. The error rate has dropped significantly since the introduction of deep learning. And then since 2015, the accuracy of deep learning has actually exceeded that of human level accuracy. I always like to point out with this graph is that the human itself is one PhD student at Stanford representing all humankind. But you get a feel in terms of how good this technique has gotten. And that's where a lot of excitement lies. One thing to also highlight is the use of GPUs has also significantly increased on this ImageNet challenge. So shown here, in terms of the green bars is the number of GPUs that were used per entry in the ImageNet competition. And you can see by 2012, only 4 entry used GPUs, and now 2014, 110 GPUs. And so this slide is courtesy of NVIDIA. They're very happy about this. But really, I think the emphasis here is to show that compute is very important to enable these AI technologies. So it's not just the algorithms, it's not just the data, it's also the compute. So you need all 3 kind of factors to enable this success. I will also just briefly talk about some of the applications where deep learning has shown a lot of success today, and then also moving forward to the future. So we just saw image classification is a very effective task that has been where deep learning has done really well. Also there's things, so image classification, you take an image, you say what's in the image itself. There's also object localization and object detection, which is more challenging. So if I give you an image, you can't just tell me that, okay, there's a dog in this image, but where in the image is the dog itself? So you have to go and search for it. So that's the localization detection. There's things like image segmentation, where I have to tell you where is the foreground and the background in the image, and this could be useful, for example, if you want to focus just on the foreground. Action recognition, so processing video itself and telling you what a person's actually doing rather than just in the still image. And also, more recently, looking at image generation. So there's been this work from Google where you can kind of synthesize just regular photos with different kind of art styles and then synthesize them together to generate new images as well. Some additional examples where we've seen basically human level accuracy or superhuman level accuracy with deep learning. So one example has been face recognition. This is from Facebook, and this is from 2014. So you can imagine it's substantially improved beyond beyond what I'm showing here. But they were able to show back in 2014 that deep learning accuracy is around 97.25%, whereas human level accuracy is 97.53%. So this is very close, and I could imagine maybe they've closed the gap by now. One of the reasons why they're very good at this is because obviously Facebook has a lot of data. Everybody spends a lot of time tagging their friends and tagging themselves, and then if it's tagged incorrectly, it gets all cleaned up, right? So we give a lot of free, clean, high quality data to Facebook to run these algorithms. So if you ever don't want them to be able to recognize, you can randomly tag things of yourself. Another Particular thing that shows kind of the power of these tools is also the fine-grained category recognition ability. So in ImageNet Challenge itself, there's also 120 different species of dogs. And they're able to show that, for example, with deep learning, you have 7 errors. This is out of maybe a few hundred images, and for humans, it's 28. Again, this human is the same PhD student at Stanford who's not studying dogs, but computer engineering. So, but still, it still shows you how impressive it is that it doesn't just detect a dog, but it tells you what type of dog it actually is. Okay. Just other, quick examples of how we're using it today. So obviously, if you use Siri or OK Google, so doing speech recognition on your phone, so that's all based on AI, and now these days most likely deep learning is what's kind of going on behind in the actual cloud itself. Natural language processing, so understanding concepts that are actually being captured and translating the language in real time. So Microsoft had a big demo about this in 2011, showing real-time translation from English to Chinese, for example. And then obviously audio generation, similar to the image here, you can actually generate audio as well. Finally, another example that happened, this was, I believe, last year, was the idea of using deep learning to play different games, so strategic games. So one of the grand AI challenges is this game of Go, which is exponentially actually more difficult and more complex than chess. So you can think of the idea as you're placing these white and black tiles, and based on the number of legal positions you can do, actually there's more legal positions than the number of atoms in the universe. So the idea here is that you can't just brute force and search for the best placement of the pieces itself. You need to have some more stronger technique. And so using deep learning, this was something that was done by DeepMind as part of Google. They developed this technique called AlphaGo, which is based on deep learning. And they were able to show that with AlphaGo, they could actually beat the world champion at this game itself, right? Some other more high or maybe meaningful applications of deep learning has been in the medical field. So people are already looking at using deep learning to do brain cancer detection or skin cancer detection and so on. So similarly, like analyzing images and data. And then there's also been a lot of hype about self-driving cars, and deep learning is playing an important role there in terms of recognizing the streets, the objects that are in their obstacles. Are you in your lane? Are you not? Okay. And then, of course, there's a whole bunch of applications that other people are looking at. So we already talked about medical. There's also in finance, people are exploring the use of deep learning, infrastructure, so safety, structural safety, trying to make sure that this building is secure, traffic, and also weather forecasting, event detection, and so on. So obviously a very important area. In particular, in this talk, I'm going to focus on image classification. We won't cover all those other topics, but it's definitely an exciting topic. And then also, if you just look at very briefly, some market trends, they believe that over the next 10 years, it's going to be a $500 billion market. Shown here on the left-hand side is looking at the rise for computer vision. That's a very important area of research that's going to be using deep learning, and just looking at deep learning itself, it's also rising very quickly. So I'm not understanding why. Okay, here. So one thing again I want to analyze, and this kind of ties more closely to my research. I think the area of AI and machine learning, there's a huge number of people working on it. So we actually focus more on how do we build hardware for it. And that's why I'm showing this quote. So in particular, as a quote from Baidu, basically today's job of training machine learning models is limited by compute, right? So we saw that GPUs was part of and played an important role for this AI revolution. If we had faster processors, we'd run bigger models. In practice, we can train on a reasonable subset of data that can finish in a matter of months. So you can have faster turnaround time that enables faster development. We could use improvements of several orders of magnitude, 100x or greater. Okay, so again, compute is very important. And so here, they're primarily talking about compute in the cloud itself, and I agree that we have to continue to innovate there. What I'm going to focus on is how can we get out of the cloud and kind of bring this intelligence locally and to the edge, as one would say. And why is that important? Well, for several reasons. So the first thing, which is very prominent these days, is privacy, right? So you might not want to share all of your data with the cloud because you may or may not know how it's going to be used, right? So especially there's a lot of personal data you might not want to share, and then also some of the applications people are thinking of is using, let's say, deep learning for vision for the blind or the visually impaired. So you wouldn't want to share everything that you're watching with the cloud itself. Another important reason that you might not want to do all the processing in the cloud is latency. So actually, there is going to be some delay between when you capture data with your sensor, you transmit to the cloud processes it, and then kicks it back to the actuation or activity itself. There's some latency there. And if you're doing something like self-driving cars or drone navigation, that delay you cannot tolerate. Or if you're running very quickly, you can't wait a second to have the actual results come back to you. Right? It can cause an accident by that point. And then finally, of course, there could be the issue where you just don't have communication. So if, imagine if you're navigating and then your internet connection just drops. I mean, you don't want your drone to just drop out of the sky, right? So you need to have, might not always have a very strong communication, or if you do have it, it's very limited in terms of bandwidth and what you can pass back and forth. Okay, so these are the reasons why you want to bring this functionality as much as possible into your pocket outside of the cloud itself. You want to be less reliant on the cloud. In particular, in the research, so now we're kind of switching. That was a high-level overview. Now we're switching to more research related to my group. In particular, in my group, we really care about video because we think video is the biggest of the big data. So if you look at the internet traffic today, over 70% of all the bits that kind of move through the internet are used to represent pixels, right? So pixels are really just dominating our communication space. You've already seen the statistic about YouTube. If you look more in terms of industrial applications like video surveillance, we're talking about over 500 million hours of video that's collected every day, right? So it's a huge amount of video, a lot of communication, and ideally, because of the reasons we talked about before, you would love to have this processing actually locally on the device, right? For the privacy, latency, and limited communication reasons. However, the issue is that on these devices, the energy that you can provide is very limited due to the battery capacity. In many of these cases, you don't want to have a huge battery because it increases weight, both for your phone or for your drone. So the default mechanism by which people do these things these days is that you actually compress the data, you send it to the cloud, and then the cloud processes it. If you've ever done any work in terms of in data centers, even on the cloud, power consumption is very important in terms of just the cost of powering your power plant, but then powering your data center and delivering that power to your data center. And of course, there's the environmental impact of that as well. So the main focus of our research is that regardless of whether you do the processing on the edge device or in the cloud, you're going to need energy efficient pixel processing. Okay, in particular, you either need to compress the pixels very efficiently, or like we were talking about, actually do the intelligent processing on the phone or these devices itself, and only send the minimum information you would need to send out. To understand what are the constraints that we actually have on these portable devices, for example, looking at video coding. So video coding or video compression is something that you would typically have on any device with a sensor, because you need to compress. If you're going to transmit or store video, you have to compress it. So what is the typical budget that we have today to do that? So the first thing is area cost. Area cost basically translates to the cost of the chip itself. So if you're a company, you care about area cost. And what typically dominates area cost is the amount of memory you actually have. So this is a memory on chip. So you're typically limited between 100 and 500 kilobytes of memory on chip. Your power budget, so typically your smartphone itself, the chip that's doing the processing has to consume less than a watt of power. Throughput, so you want to have real-time processing, right? If I'm capturing video, I want to be able to compress and send it in real time at 30 frames per second. I want to be able to play back video 30 frames per second. And of course, energy in terms of how much battery energy you're taking. Your energy per pixel works out to be, when you factor in power and throughput, to about 1 nanojoule per pixel. So in my group, we've already kind of looked at a task of object detection on chip. We published this work in 2016, and we were able to show, shown here in red, compared to the video coding work for various different video standards shown here in blue, we were able to show that for the same amount of energy, we could actually, tell you what's in this image, where are the people located, where are the cars located in this image, and at what scale. So we can already kind of do that today. This is with a type of artificial intelligence based on the handcrafted feature approach. Now the question is, as I mentioned, that we really want to increase accuracy using deep learning. And the question is whether or not we can achieve this efficiency with deep learning itself. Another thing I just want to highlight is the difficulty of actually understanding images itself as compared to video compression. So if I showed you this image, could you guys, who here in the audience can recognize what this image is, just with a show of hands? Just to make sure you guys are right. All right, A's for everybody. So can you guys call out what it actually is? What is this object? Cat, all right, that's good. However, if you were a computer, you would not see this image. You'd actually see just a bunch of numbers. And if I showed you a bunch of numbers, that would be a much more difficult task to do, right? And tell me, like, what is this object with a bunch of numbers? And that's what the computer sees. With compression, you can compress this easily, but you could imagine then computer vision is a much more complicated task than video compression and requires much more compute. Okay, so that's why it's not as easy to say, ultimately what we want to do is make computer vision as efficient as video compression. It's not an easy task to do. All right, so this is where the Iris chip comes in. So this is some work that we did at MIT. It's led by my student Yushin Chen, and it's with my collaborators Tushar Krishna and Joel Emmer, and this published last year. And basically we're looking at energy efficient hardware for deep convolutional neural nets, which is a type of deep learning for image processing. So now it's going to get a little bit more technical. Before is kind of the intro. So we're going to go deep now to understand how we can actually make this more energy efficient. Okay, so again, a more deeper tutorial on what actually convolutional neural networks are. So we kind of saw before, basically, we're looking at a bunch of multiplies and accumulates, again, these neurons that are emulating the brain. Actually, in deep convolutional neural nets, we have multiple layers of these multiplies and accumulates. It goes very deep. And again, we're going from low-level features to high-level features. And these days, we're talking about up to 1,000 convolutional layers. And then typically, it's followed by a bunch of fully connected layers. But let's not get into that today. What you should really take away is the computation of convolutions account for over 90% of the overall runtime and energy consumption. All right, so a very brief kind of 101 in terms of what is actual convolution itself. So if we have an input image shown here, it's a 2D image, or we can call it a feature map, and then we have a 2D filter where the weights of this filter are learned by the data. What we do is we take this filter and we apply it to this image. Basically, we do an element-wise multiplication, so each weight is multiplied by each pixel at a certain location, and then we add up all the products together, or partial sums together into one value, and that will be the output pixel. And what we do is we basically slide this filter like a sliding window across the input image, and we get multiple pixels. And this would be the traditional way by which you would do just any type of regular image processing. Okay, so we've done this for years. I teach an image processing class. This is in a textbook that's like, in the 90s or in the 70s, you'd still do this. So this is nothing new. What makes CNNs or deep learning more complex is the increase in dimensionality. So rather than just doing this 2D convolution, you have a third dimension, right, which we refer to as channels in this case. So rather than just doing 1D, we're just doing now 2D convolutions across multiple channels, and then we have to add up all their values to generate one output value. And the channels themselves can be quite large. So at the very first layer, you can think of the channels as 3, so red, green, and blue components of the image. But then as you get deeper into the network, it gets quite large. So for example, if we look at AlexNet, which was the first network that used deep learning for that ImageNet challenge from University of Toronto, it had up to 192 channels. So the dimensionality there is quite high. And then in addition to having these high dimensional filters, we also have multiple filters as well. So we're talking about 96 to 384 filters that you're going to apply to the same image. Okay, so dimensionality grows, and of course, realistically speaking, we're going to process more than one image at a time, so we typically process multiple images to generate multiple outputs. The thing that you should take away here is that the filters in AlexNet, again, using it as an example, the size of the filters will change depending on what layer you're doing. The number of filters will change, and the number of channels will change as well. And so from a hardware point of view, what's really important is that you need your hardware to be flexible enough to support all these very different sized filters. And then in addition, of course, what I really want to emphasize is that per layer, you're doing hundreds of millions of multiplies and accumulates. You have tens of thousands to almost 1 million parameters per layer of computation. And this is just to process one image, one very small image. Okay, so the amount of computation and amount of data is huge. However, there are properties that we can leverage, so everything is not lost. High throughput is possible because we have high amount of parallelism. So all these multiplies and accumulates can happen at the same time. So that's great. In theory, you can not infinitely, but very, very highly parallelize the system. The challenge actually, in particular in hardware, is how do you actually bring the data to the actual compute engine? So if I have this multiplying compute engine, I need to read the weights and the pixels and the partial sums from somewhere else, and I need to bring it all the way from very, very far away external memory all the way into the chip, and particularly the location of where the multiply and accumulate will be within the chip. And that actually is the bottleneck both for throughput and in terms of energy. So if we are reading all our data from DRAM, which is a type of off-chip memory, it actually takes 200 times more energy to bring that data in than to actually do the multiply and accumulate. Okay? And we typically, for each multiply and accumulate, we saw that we had 4, basically reads and writes from memory in order to do that. Fortunately, again, things are not all at loss. So there's all these what we call reuse opportunities, meaning that we bring a piece of data onto the chip, we can reuse it multiple times as possible where it's stored cheaply in a low-cost memory. I won't get into too much detail, but you can have what we call convolutional reuse, where on the same channel you're using the same pixels and weights just in different combinations. We applied multiple filters to the same image, so you can also reuse the filters. The pixels in the image, you can imagine you read that once onto your chip, and then you can use it across multiple filters, and then vice versa. A single filter will be applied to multiple images, so you can use that filter information over and over again. There's 2 different kind of hardware architectures that you would use to process this information. One is a temporal architecture. This is much more similar to SIMD or SIMT, which means GPU or CPU. This is the typical architecture you would have. The idea is that we have many ALUs, or arithmetic logic units, many processors. They share the same control, meaning they have to do exactly the same thing, and then they read and write to a large shared memory. Alternatively, with specialized hardware, which is what we're looking at, you can have what we call a spatial architecture, where you have each processing element, or ALU, will have its own control, meaning all the processors can do different things, and it also has its own local memory, meaning it each has its own memory that belongs to itself, and it can also share data with its neighbors. So sharing is good, right? Because your neighbors are much closer to you than going off chip. I mean, maybe that's a philosophy in life. Sharing is good. Okay. And so the major ideas here is that you have efficient data reuse. So if I bring something onto the chip and I can bring it into the ALU itself, I can actually read from my own local small memory, or I can share it with my neighbors, and that's much cheaper than to bring the data on again every single time. And so that's kind of the main advantages, both the efficient reuse of the local storage and the communication amongst the neighboring processing elements. And so the real question that we have is, how do we take this very high-dimensional convolutional neural network with millions, hundreds of millions of parameters, and bring it onto the chip itself and map it to this spatial architecture? Now remember, as I mentioned, for video coding, like our typical multimedia chips, you only have about 100 to 500 kilobytes of memory, but you're talking about millions of parameters. So you can only bring a small subset of that network onto the chip itself. And so the question is, how can we bring that on? So at a very high level, another thing I just want to emphasize is looking at how we move the data through the system. This is kind of relates to how much data we can actually reuse. In most memory architecture systems, what you do is you start out with a very low cost energy in terms of the ALU itself. So you do a multiply and accumulate. Let's say it has the energy of 1. If I'm reading from the small memory close by, it's going to be 1x. If I read from my neighbor, it's going to be 2x. We also have a larger buffer that you can store on chip. That would be 6 times the energy. And then if I go off chip, it's going to be 200 times the energy. And so the whole challenge here is that if I bring something on chip, I want to be able to read that data from these very low cost memories as frequent as possible. So I want to do only one transition from the DRAM to the buffer, because that counts 200x. And then basically I want most of my data to come from locally over here. Just keep on reusing it over and over again from this low cost memory. Very briefly, I'm going to talk about, people have explored various different ways in which they can do this. We noticed that there were 3 different types of data that people had. Remember, we had the weights, so weight of the filter. We had the pixel information, so image information, and then some of the partial sum that's computed in red that was generated. So one strategy some people have is like, okay, I'm just going to bring the weights and put all the weights of the filter in the small memory that's located in each of these processing elements. The trade-off is that the partial sums and the pixels have to move around, right? So you have one set of data that's local, but the other ones have to all move around. So those are going to consume a lot more energy. The alternative strategy is to say, okay, I want my partial sums, which is another type of data, to be stored locally within these processing elements. And instead, now the pixels and weights are going to move around and consume a lot of energy. And then the third strategy is to say, okay, these if you look at memory design, the smaller the memory, the less inefficient memory is going to be. So basically the idea is that in a small memory, each bit requires more area. So I'm just going to get rid of these small memories and then use that area to make a really large global buffer. So overall, my chip stores more bits, but then everything else has to like shuffle around now. So I won't go into the details. So our solution is to actually, rather than, you'll notice that in each of these, basically they're focusing on one specific type of data, right? So either the partial sums or the weights or the off-chip bandwidth. So in our approach, what we call the row stationary approach, we actually allow for both the weights and the inputs to be stored locally in the processing elements. And we exploit what we call 1D convolutional reuse within each of the processing elements. And then we also allow the elements to share a minimum amount of data, the partial sum data. And so the main takeaway here, that's very technical, the main takeaway is that we really optimize for overall energy efficiency as opposed to one specific data type. Okay, so this will extend to a higher dimension, which I won't get into, with more reuse by mapping more rows to each PE. And then finally, if we look at the energy, so this is all the different types of ways that we did the mapping. So we saw the weight stationary, output stationary, no local reuse. The row stationary approach, where you really just optimize for overall energy efficiency as opposed to one particular data type, gives you about 1.4 to 2.5x lower energy than just optimizing for a single type of data type. So that's basically emphasizing that. So what we want to do is actually build hardware to demonstrate this type of data movement. And so this is where the Iris chip comes in. So this is the Iris chip. So some of these things should look kind of familiar. We have the processing array here by 14 by 12, 168 processing elements. And they can communicate to each other as well as go off chip. Another factor that we introduce, okay, so, all right. So another thing that this chip can do is it's also adaptive. So if it sees, what tends to happen is a bunch of the data that the chip is processing ends up being 0. So what can it do? It can exploit this. First, it can compress the data, so it requires less storage, so less data movement. We said that moving data is expensive. We do compression and we avoid that. The other thing is that when the data is 0, it also skips the processing. Right? So if it's like, oh, it's 0, I'm not going to do any processing, I'm not going to read anything else from memory, and it can save almost 45% of the power, or almost half of the power. So here's a die photo of the chip itself. So it's actually pretty small. So this is 4 millimeters by 4 millimeters. We've kind of just blown it up so you can see it. It can do a wide range of the different filter sizes. This is in TSMC 65 nanometer technology, which is actually quite an old technology. So these days, if you look at more advanced process nodes, we're talking about 10 nanometers. So you can imagine if you used smaller devices for this, it would be even more efficient. In the time limitation, I won't talk about this, but okay, actually, I might just mention. So if you were going to do 2.6 billion multiplies and accumulates, originally it would require 16 gigabytes of data inputs and then 5 gigabytes of data output. But since we're reusing a lot of data on chip by sharing with your neighbors, let's say, you only require 800 megabytes of data in the buffer, and then you only read from off chip 15 megabytes. When we compare it to a GPU, which is the typical, well-known platform that people use currently for neural networks, particularly a mobile GPU. So it's designed for lower power. In this case, we're looking at NVIDIA's TK1 chip, and this is in an older process technology. So you can imagine if it's the same process technology, it would do better with a similar processing and similar amount of memory. We're looking at half the throughput, but 20 times lower power. So we're talking about 278 milliwatts versus around 6 watts in the difference, right? So if you have basically half the throughput, but 20 times lower power, you're talking about basically 10x more energy efficient. And you can see the DRAM bandwidth is quite a bit lower. Okay, so in the interest of time, I won't show this video, but we have integrated, maybe I should show it. We have integrated the chip itself into an actual system that can do a recognition task. So basically what you can do is you can grab a picture of a dog, let's say a corgi, you send it to the chip. Right, so here's the chip running, it's just showing that's around under 200 or 300 milliwatts, and that's the chip itself. And then when it comes back, it properly classifies that that is in fact a dog, and it can also tell you, the type of dog it actually is, in this case, a Pembroke. right? So this is just showing that, so the innovation of the algorithm comes more from the whole machine learning community, and we're just showing that we can run that algorithm with very low power consumption. So in summary, at least for the Iris chip, we have this reconfigurable accelerator, supports a wide range of neural network hardwares. We have various different mechanisms to reduce its energy, and we've integrated it into an actual system itself. But one thing that we talked about before is that we really want to see if we could make recognition as efficient as video compression. So if you look at this plot here, accuracy is shown here on the horizontal axis, on the vertical axis its energy. You can see that it's still kind of for linear increase in accuracy, you need exponential increase in energy. Right, so really, and the video compression is here at 1 nanojoule per pixel. Even with this really highly optimized hardware, we're still looking at 100 times to over 1,000 times more energy per pixel than video compression. So the question is, can we reduce this even more? So we have this new work recently looking at not just the hardware, but the algorithms itself. Right? So in particular, typically in research, it's actually two different communities, the people who design the hardware and people who design the networks or the algorithms. And so we wanted to bridge those two communities and basically have a way in which the algorithm designers can actually estimate how much energy their algorithms would be and kind of feedback so that they can design their algorithms to make them more hardware friendly. So it's kind of this co-design space. And so we've designed this tool that can take an algorithm, any neural network, and tell you exactly how much energy it's kind of consuming for the different layers within the network itself. And this has shown to give you an additional 3.7x or 1.6x reduction, shown here in the red, compared to the blue in terms of, so in this case, the steeper the slope, the more efficient it is in terms of, it means lower energy for higher accuracy. And so we've shown here that the red kind of moves the graph over while maintaining accuracy, by basically feeding back this energy information to the algorithm during the design process. Okay, so we'll get into that. And then finally, one of the projects which also is kind of related to this work that we're looking at in my group now is really, can we do real-time navigation on these nano drones? This is in collaboration with Surtesh Karaman, who's also an AeroAstro. And so we have, commercially there's these really nano drones, these very small drones that you can kind of navigate with, a remote controlled device, but basically they have no intelligence in them. They're just told what to do. And the question is, can we actually put this intelligence onto these very small drones? But the key thing is that you can't have a very big battery, and you can't mount a mobile GPU, which is, in the tens of watts. That's too much for the drone like this. So really what we're looking at is building very energy efficient chips that we can store onto these drones, leverage this intelligence. And so you can imagine these drones could be used for things like search and rescue, where you don't have any Wi-Fi connection. You can't rely on the cloud to actually navigate and search and try and find people after these big disasters. So it's always important to acknowledge the students who do the majority of the work. So this is my group in the Energy Efficient Multimedia Group, Systems Group, and these are all the sponsors that we have for this work. And that basically concludes my talk. So we have a lot of this stuff is obviously available online. So if you're interested, you can just go download and learn more about this exciting area. Okay, thanks.